Okay. I should have made that one the real quiz instead of the little short one. Okay, so those problems are due on Monday. They're graded homework problems that we need to practice with a little bit of pressure. The mechanisms that you're probably going to have to learn about, or probably going to have to do for the exam, which is a week from this coming Monday. The Monday before spring break is exam 2. So those will give you some practice problems in writing mechanisms. And so make sure when you look at that, that you do the, that you give me what I'm looking for. So for the first ones, there's just transition states if it's SN2. And for the last batch, just transitions, or just also include the resonance structures and the resonance hybrid. And that's what we're going to do today is 1, 2, and 1, 4 edition. So any questions to start with? All right, so I will start with this then. We're going to start with that reaction. And the first question that I'm going to ask is, where should I, first of all, this is a symmetrical molecule. So adding H plus to A or B, it doesn't matter whether it's the top A or the bottom A, or the top B or the bottom B. So my question is, we're going to add H plus to a double bond. Where are we going to add the H plus? To A or to B? Okay, I'll give you a minute to think about that, and then we'll poll. So where am I going to add the H plus to this? Am I going to add it to A or am I going to add it to B?
Yeah, that's what I was thinking about. What number is like age, do you know what I mean? I don't like that.
Does everybody have their little color A, B, C, D cards?
Yeah.
No, who doesn't have them? Okay, if you have that, let's use it. If not, A is 1, B is 2. Okay, so which carbon should I add my H plus to? Carbon A or carbon B? Add it. Although it could be. What do we got? A C means what? Okay, I'll take the depends for C. I might want further clarification on that, but it means. So I see a few A's, some B's, a C that it depends. What does it depend on? The conditions. Let's see about that. Okay, so let me write the products that you would get from adding the H to carbon A and adding the H plus to carbon B. And again, since this is symmetrical, it doesn't matter whether I add the H plus to the top A or the bottom A. I'm just going to add it to the top A. So there's our two carbocation intermediates. Give me a reason why you chose to add to A. If you had an A sign up. Why did you choose A? Don't give up so easily. That wasn't my question. My question was, why did you choose that?
Well, I think that A forms an allylic carbocation versus B.
Okay. So A forms an allylic carbocation. What's the reason for B? Because it's forming a tertiary carbocation. So which one of these is more stable? The allylic secondary carbocation or the tertiary one? Now, hold on to your answer. Let's write the structure of the allylic carbocation. So which one of these is more stable? A or B? What do we think? Yeah, you can always do that too if you have a spare piece of paper. You can always write A or B on it. I'm seeing a lot of A's. I'm seeing how many B's? You're on your own. Okay, hang on. Reason why A is more stable? It has two resonance structures. But does that be a tertiary carbocation? It will if one of the resonance structures is a tertiary. So in both of these cases, we have a tertiary carbocation. Now, if you're saying that the double bonds are not equally substituted, okay, what did I say last time? Predominantly, what's going to determine the stability is the carbocation, whether it's primary, secondary, or tertiary, and the double bond stability will play a minor role. If you had two tertiaries and one had a double bond that was more substituted, I would give it nod, but here there's two resonance structures, one of which is tertiary. Up here there is only one. So where does the H plus add? It's going to add to A. Now, why did I give you this problem? Because it's kind of an exception, but it's not really an exception. So with this, with the molecules, with dienes, if I'm going to do 1,2 and 1,4 addition, notice that it was, what does 1,2 and 1,4 mean? Well, if I want to number these carbons, I'm going to always count 1, 2, 3, and 4 as the 4 carbons in the diene, in the two double bonds. And notice it's not 2,1 addition, it's 1, 2, or 1, 4 addition. So you always add the electrophile to the end of the double bond system, carbon 1. I will always give you a symmetrical system, so it doesn't matter whether there's no 2 carbon 1s. If it was unsymmetrical, then we'd end up with 4 products on 2. So I'll give you a symmetrical diene. So we always add to the end. Why? Well, it's not quite Markovnikov's rule, because Markovnikov's rule would be to add to carbon B. If this was just the double bond here, I would add to B because B has more hydrogens. But it's a diene. So we always add to carbon 1. We always add to the end because then we make an allylic carbocation which has more resonance structures and is going to be more stable. So it's not the literal Markovnikov rule about greatest number of hydrogens gets the hydrogen. It is sort of the overarching Markovnikov rule, which is add the electrophile to give you the most stable carbocation intermediate. And so Markovnikov addition, again, if this was just this double bond and this one wasn't here, you would add the B, but this is not just an alkene, it's a diene. So we always add the H plus to the ends. And this system is set up to try and trick you, which I did, into adding the H plus here because our normal thing is a tertiary carbocation is more stable, but it's not allylic. So the allylic carbocation is more stable because of the resonance structure. So we always add the H plus to the end. To carbon number 1. So we always use 1, 2, 3, 4 for the diene. Does that make sense? So in the video or in the book, I'm sure in the video I said always add to the end. And the reason for that is because that will make the most stable carbocation. Okay, does that kind of make sense? So then B's out. So that means for A, I'm going to now take my Cl minus, add it to that carbocation, take my Cl minus, add it to that carbocation, and then I'm going to draw my two products. And again, we're treating the intermediates as if they were the true intermediate, or the resin structures as if they were the true intermediates. So there's my two products. I will call them a new A and a new B. So my next question is, what is the kinetic product? Is it the new A or the new B product? Which one of those two is the kinetic product? A or B? The new A or B? Or one or two? I see a couple of A's, some B's. So which one is the kinetic product? Right? So the kinetic product comes from the most stable intermediate, which is which one? B. All right. So this is the most stable intermediate. So that's going to make B the kinetic product. Which is the more stable product? Whoops, sorry, I left the methyl group off there. That's important. So which one's the more stable product? And it's not automatically the other one. You should check it. So in this case, that's more substituted. That's the more stable product is A. And so therefore, A would be the thermodynamic product. So this is the kinetic product. This is the thermodynamic product. And you should always check them just to make sure that it's not a strange case where there's only one product or both of the products could be. So on the exam, I can do one of two things. I can ask you to write the mechanism, which I will, including the resonance hybrid, which we'll do in a moment. Or, and I could ask you just to write the kinetic and thermodynamic products of the reaction. And I'll show you another way we can write the mechanism, or just do the 1, 2, 1, 4 addition directly without writing the mechanism. So that's how we get the kinetic and thermodynamic products. And I can even be more sneaky than that and just say, give me the product that exists under high temperature, long reaction time conditions, so that you have to know that as well. what would be the resonance hybrid for this? So for the resonance hybrid, I'm going to write in all the sigma bonds. Every place there was a positive charge, there will now be a delta positive charge. And the dotted lines, the partial bonds, will be between the two delta positive charges. So that's a resonance hybrid. Again, it's taking the average of the charges and the averages of the bonds. But in this case, there's kind of a pattern that you can use, and the pattern would be that we have the delta positives wherever there's a positive in the resonance structures, and then the dotted lines go in between. All right, so does that make sense? So I could ask you to do that. Well, why do I say I could? I will ask you to do that. All right, that's being prescriptive. Other universities, they wouldn't tell you that. But if you had any instincts, you would know that that's what's going to happen. Well, you wouldn't have any older exams unless you were in a group that kept track of all the older exams, which never happens at those kinds of schools. But I give them to you for free to get stopped. There's only so much creativity that I have. Even though you think otherwise, really there is only so much creativity I have. Now, one thing you do not want to waste any space up here with is 1, 2 is the blank product, because you have to take it on a case-by-case basis. In this particular case, the 1, 2 product turned out to be the thermodynamic one. But I can very easily switch that by coming up with a new problem. And again, doesn't take a lot of creativity. It takes a little bit to say, what would be the kinetic and thermodynamic products of this reaction? Now, the reason I'm doing Br2 is because we're going to treat Br2 as if it's a Br plus and a Br minus. That's what we're going to treat it as when we're writing the mechanism. So I know we have the bromonium ion, but the problem is the bromonium ion might be able to stretch between carbons 1 and 2, but it will not be able to stretch between carbons 1 and 4. So it's probably a good question as to where if there is really a triangle in this or not, but we're not going to worry about that. So first thing I would do is I would say carbons 1, 2, 3, and 4. If you want to work from the bottom, that's perfectly fine. It's a symmetrical molecule. What am I adding? I'm adding 2 BRs. So if I'm just writing my product, I'm going to add a BR 1 and 2 and add BRs 1 and 4. The tricky part is when you go 1 and 4, you've got to make sure you move the double bond between 2 and 3. So I can write the products directly. I can say, okay, bromine on carbon 1, bromine on carbon 2. There's the 1,2 product. Bromine on carbon 1, bromine on carbon 4. Double bond between 2 and 3. There is the 1,4 product. And I'm going to show you another way you could write the mechanism if writing the mechanism from the beginning doesn't quite make sense. You can actually, if this makes sense to write the products this way, we can work backwards on the mechanism. So I'm showing you more than one way. It's up to you to figure out which one works for you. So where did those products come from? The 1,2 product came from having the bromine attached to carbon 1 and a carbocation on carbon 2. Where did the 1,4 product come from? It came from having a bromine on carbon 1 and the carbocation on carbon 4. And then how did we get that? We had the Br minus come in and add to both of those carbocations. So I'm just kind of working from the 1, 2 to get me the mechanism.
Do you have to get like a macro sheet or something in order to get the 1 4? Because I was just expecting mechanism for
No, you would not get, no, there's no shifting going on. There's a shifting of the double bond, but not of any atoms. So this is what happens. So between those are two resonance structures. How do I get from the compound on the left? I move the arrows, I move the double bond that way, leaving the positive charge down here on 4. I can also put the arrow in to then show how I would get from carbocation on 4 to carbocation on 2. Well, for this problem, forget about the triangle. That's a good question that I don't know the answer to. Like, I would expect the 1,2 product to be 2 bromines trans, but I have no idea what the 1,4 product would be. Because I don't think the bromine can surf those 3 bonds. That's a very good question that I don't know the answer to. So those are the 2 resonance structures. Resonance hybrid, what would it look like? Again, the resonance hybrid is always written by adding the electrophile to carbon 1. There's a delta plus charge there, there's a delta plus charge there, and then dotted lines all the way around between the 2 delta plus charges. So that would be the resonance hybrid. So I'm just treating the Br as a Br plus, like an H plus, in this case, which is the easiest thing to do. I figured there was some mistake. Can only happen more. The only thing I'm missing with making this the mechanism is to do this. Is to add the pair of electrons to the Br plus and then break the bromine-bromine bond to make the Br minus. And in the previous one, I think I'm missing that arrow to go to the H plus. So in the previous one, which I'll go back to here in a moment, I think I'm missing that arrow, so I'll go back and put it in. So let me go back and put that one in because it should look like that. There should be an arrow from the double bond going to the H plus. So in this case, we've got the 1,2 product A, the 1,4 product B. Which one is the kinetic product in this case? Is it A, 1,2, or is it B, 1,4? Which one is the kinetic product? So which is the more stable intermediate? And which is the more stable product? B is thermodynamic product. A is kinetic. And the positions of the methyl groups here are, if I would have started with this problem, everybody would have added the H plus or the Br plus to carbon 1. Hopefully from now on everybody adds the electrophile to carbon 1 regardless, because that's where it goes. Okay. So in this case then, what we have is we have a 1,2,1,4 addition from the diene. You have practice mechanisms, which are probably eerily similar to this one. What kinds of things can I add to the double bond? I can add HX. I can add a Br2. I can add an H plus H2O. And since I can add H plus H2O, I can add H plus ROH. So those are the 4 things that we could add to a diene. And they would all do 1,2,1,4 addition. The H2O and the ROH would each have an extra step, because when you form the carbocation, the water comes in and adds, and then you lose the H plus. So there's one additional step with H plus H2O that there isn't in the other ones. So this is pretty much what we did on Monday, except it takes an extra step to get the allylic carbocation. So that's why I did Monday, was to go over the nitty-gritty stuff, and then this one it's like, oh, it's the same thing, basically. We could draw the same reaction coordinate diagram, which are in the PowerPoint notes, as well as I think I go over those in the lecture, so it's pretty much the same thing. So this is kind of the end of the 1,2,1,4 edition, which is the first half of chapter 19. Does that kind of make sense? So you'll have some practice problems to get some practice with that. The second half of this chapter 19 is dealing with Diels-Alder, which some of you did in lab yesterday, some of you will do in lab tomorrow. A Diels-Alder reaction is to take a diene and add to it an alkene. So this is a Diels-Alder. So in general, when we do a Diels-Alder, I like to number the 4 carbons of the diene, and then I number the 2 carbons of the alkene, 5 and 6. Okay, so that's the way I'm going to do this. And in terms of the arrows that go through this arrow goes like so. The bond between 3 and 4 is used to form the 4,6 single bond, and the bond between 5 and 6 goes to form a bond between 5 and 1. So, and the arrows could go in opposite directions as well. That gives us a transition state that looks like this. A partial bond between carbons 1 and 5, the way I've drawn it, and 4 and 6. And then there are partial double bonds the rest of the way. So it kind of has a benzene ring type look to it. And then the final product here, the thing to remember about a Diels-Alder is that you've got carbons 1, 2, 3, and 4, and 5 and 6, and then there's a double bond between 2 and 3. In organic chemistry, the premium has always been on forming carbon-carbon bonds. That's always been the premium. And so anybody who did that previous to like 1920, you know their name because it's in every organic book. Since then, yes, they all are named reactions, but we don't know all of them because some of them are beyond the scope of this class. But it's always been a premium to form carbon-carbon bonds. I give you Grignard. This one forms two, and so it's twice as important because not only does it form a double, or not only does it form two carbon-carbon bonds, it forms a ring. And we'll talk about this on Friday. Plants do this all the time. They do these reactions to put these molecules together. And you can actually do this to form a steroid as well. So putting these 6-membered rings together by Diels-Alder is important. Diels was a German chemist, Otto Diels, and then Kurt Alder was one of the first famous organic chemists that was an American. Organic chemistry is not an American science. It was developed in Germany. A lot of it was developed in Russia. I give you Markovnikov and Zaitsev. But the Russia in the early 1900s and stuff, there was a lot going on that nobody really knew about. So it was not as closed off a society as maybe China was, but it's only some of the Russian stuff has come into play since. But really, organic chemistry was German. And if you wanted to really study organic chemistry, you had to go to Germany. When I went to graduate school, before I got there, the requirement was you had to have a working knowledge of German if you wanted to do organic. So I took my 1 semester of German, second semester senior year, and I got there and they dropped the requirement. So, and I went to a state school, which means I didn't have to be fluent in any languages when I was done, or fluent in any philosophy or religion either. So, this is Diels-Alder. So I'm forming a 6-membered ring. There's a lot of rules for Diels-Alders, just a couple of them to start with, and then we'll get into more of the rules on Friday. Number 1, the conformation of the diene has to be S-cis. Not cis, S-cis. So what's the S stand for? It stands for sigma. What does that mean? There is some rotation available around the carbon-carbon single bond. And that's the S, that's the sigma part. So this would be S-cis, and this would be S-trans. The reason for the S-cis conformation having to exist is because if you write out the pi or the p orbitals and the pi bonding for the diene, that's S-cis. And so these 2 carbons on the end, carbon 1 and 4, have to be spaced so that they can plop right on top of the double bond. So if it's S-cis, it's easy to overlap those sets of orbitals because the spacing is just perfect. If it's S-trans, the 2 end carbons are too far away. There's too much space and it won't fit the double bond perfectly. So that's actually, it's the orbital overlap. That's how it occurs. And there's a lot that goes into Diels-Alder that we're not going to talk about in the book because we're not going to go into molecular orbital theory and all of that stuff. But there's a lot more complicated rules. There's Woodward-Hoffman rules. There's a whole bunch of stuff that maybe I'll allude to on Friday. So that's rule number 1. That conformation of the diene has to be S-cis. What if it's S-trans? Apply a little heat, it'll swing around, form S-cis, and then react. You can get it to react better if you hold it there, which is what you would do with the ring. The second rule is that the stereochemistry of the double bond is preserved in the product. So what does that mean? Well, in this week's lab, we are taking and making butadiene by basically cracking sulfolane, by thermally heating it and getting rid of the sulfur dioxide. We're forming the butadiene, and we are reacting it with maleic anhydride, which is that. Now, the maleic anhydride is locked into a cis conformation, which means that the product that we're forming is going to have the cis conformation, or the cis conformation. Going to have the two groups, cis in the 6-membered ring. If the double bond, if the diene was reacting with a trans double bond, then the product we would make would have the CN groups trans, because that's what they were in the alkyl. And the reason that I put 1, 2, 3, 4, 5, and 6 on there is because basically if I'm doing this reaction, I know the product that I'm going to make has 1, 2, 3, 4, 5, and 6 on it. So that's just a question of what's attached to carbons 1, 2, 3, and 4? Nothing, except H's. What's attached to 5 and 6? Then I can just add the 5 and 6 group. The same thing would be true down here. Carbon 1, carbon 2, carbon 3, carbon 4, 5 and 6, and then 1, 2, 3, 4, 5, 6. So the stereochemistry of the double bond is preserved in the bond. Now, does anybody think that the bottom reaction is the one with the CN groups is a no reaction? So I'm going to clarify by potentially confusing. I probably shouldn't do that anyway, because it'll probably come up somewhere. Sometimes when we first do this and I first give you reactions, people will go, "You can't do this reaction." I just did. I'm in charge. Why can't I do that react? Oh, because this is trans, and you said trans. No, I didn't. What did I say? Trans will not. It has to be S trans in the diene. Okay? So sometimes people get confused. Hopefully nobody here will get confused. But sometimes people will say, well, that's trans. Yeah, it is. But the restriction over here is that the diene has to be S. Or if it is S trans, it won't be. Whatever the stereochemistry is, cis or trans, it will react and it will be transferred into the product. Because the diene is going to cooperate down on the double bond. It's not going to go, oh, well, let's form this bond, and then a few minutes later, let's form this bond. No. Both bonds form at the same time, which means whatever the double bond was, it's stuck. So that stereochemistry is going to be locked in from this. So the first two rules are S cis, not S trans, and the stereochemistry of the double bond must be preserved. Okay? So for Friday, I'll send out the list of topics, but the list of topics will most likely be writing a 1,2,1,4 product, maybe telling me whether it's thermodynamic or kinetic, and then writing a Diels-Alder product, which would be writing those. And I'll try and come up with some practice problems and throw those up. All right, so if you have any questions, put them up on Piazza. Come and see me. If you want your quizzes from last time, Caitlin, Jenna, Ben, Emma, they are not in alphabetical order, but they appear to be in order of that size.
No.
Emma, Olivia, Katie, Catherine, Caitlin, Grace, Christian, Sarah, Alicia, Catherine, Emily, Haley,
Because I was about to say.
Grace,
That must be
Jenny,
I'm very
Yola, Anna,
Girl, what'd you get?
Julia, Noah,
Yeah.